Hi everyone, so today I'll be talking about the Mathematical Analysis I, the Archimedean Property. So for a small introduction, the Archimedean Property plays a very crucial important role in mathematical analysis, especially analysis. So it can be easily used in the inequalities and also real number system, and also can be proving using epsilon delta proof and approximation arguments and real number analysis and more. So it's very important to learn it. So before learning it, we need to know some background of the theorem. So before learn, we will now introducing the theorem 1. The set of positive integer z plus is not bounded above. So we were using a contradiction to prove it because it's more easier. And so we want to show that the set of positive integer is bounded above. So we will have a set S. S is the positive integers, and here I have a hint, completeness axioms. Completeness axioms that tell us that set S is not empty and is bounded above, so there will exist an M, which is the upper bound. So for this case, S is not empty and it's bounded above, so it can use completeness axiom. So there will exist an M, which is the least upper bound. And therefore, we know that M is positive integer, so M must be larger than M minus 1. So this is true. And we know that M minus 1 is not a least upper bound, because M already least upper bound, so M minus 1 is not. And if M minus 1 is not a least upper bound, so there will have an integer larger than M minus 1. So N will larger than M minus 1. So we move the minus 1 to front, so N plus 1 larger than M. So there is a positive number larger than M. So it's contradict to the M, which is the least upper bound, because least upper bound cannot have something larger than that. So it's contradict. So we prove that the set of positive integer is not bounded above. So this is a very easy proof. So now we will learn our Archimedean property. There we have 3. Now we learn the number 1 first. For any positive number n, there is a positive integer n such that n larger than m. This is very related to the proof just now. So we will prove using also contradiction. So there exists a positive m, and for all positive number n smaller equal to the m. So we know that, from this information we know that m is upper bound, the least upper bound. So it's upper bound. So it's proof that z plus is bounded above, right? It's bounded above. And we already know that z plus is bounded above and is contradiction to the theorem 1. So actually this already proved. So we already proven that for any positive number m, there is a positive integer n such that n larger than m. So we're just using a very easy contradiction proof by theorem 1. Because z plus is bounded above and m is upper bound, so it's a contradiction from the theorem 1. So it's very easy to prove this Archimedean property 1. We will always use this property and to prove another Archimedean property. So now let's see Archimedean property 2. For any positive number epsilon, there is a positive integer n such that 1 over n smaller than epsilon. So how are we gonna prove this? So we will let epsilon larger than 0 because it's positive, and there exists a positive integer m. So we choose m equal to, we don't want to choose first because it's very hard to choose at first. So we now revise back to the Archimedean property 1 first, because it's very similar. So there exists an positive number n such that m larger than m. So what's the related? We now look back to the Archimedean property 2. We need n 1 over n. So we need to create a 1 over n. So we can know that n is larger than m. So remember here still empty. We still need to choose m. So we choose m equals to 1 over epsilon, because if I choose 1 over epsilon, so I will get the inequalities n larger than 1 over epsilon. So this is what we already proven this Archimedean property 2, because we just need to let to the n and the epsilon change the place. So epsilon will larger than 1 over n, which epsilon and the n also positive integer, so does not affect the inequalities. So therefore shows that epsilon larger than 1 over n. So we proven the statement is correct. However, there is a general form of Archimedean property. So we now look to the property, Archimedean property 3. For any xy in the R, which x larger than 0, there exists a natural number n such that nx is larger than y. So we now prove it. We prove it in 2 cases, because the y is in real number, so we doesn't know it's positive or negative. So we split into the 2 cases. The case 1 is y is smaller equal than 0. So we know that y is smaller than 0, and when the positive real number and n is an n natural number, nx should be larger than 0, right? Because n and x also integer, a positive integer. And we know that if nx is larger than 0, so y is smaller than 0, smaller equal than 0. So nx will be smaller equal to y. right? nx will smaller than 0 and smaller equal to y. So we prove that nx is larger than y. So is it easy? And for the case 2, y larger than 0. Y larger than 0 is more complicated because we need to use back our Archimedean property 1. So we now choose back our inequalities, and x is larger than y. So we now let the x move to the right side and we get n is larger than y over x. So we know that x is a positive number and our n is also a positive number. So y must be also positive number. But how are we going to prove it? So we need property, our Archimedean property 1 from Archimedean property 1. So there will exist n e which is positive number, positive integer, and we have an n, right? We have which is n, because when we know that positive integer also including in n, right, in the natural number set. So after that we know that there will also have m larger than 0 and such that n larger than m. Now we're gonna choose our m. So look back to here. This is Archimedean property 1, right? N larger than y over x is our Archimedean, right? So we choose m into y over x. So it holds. The Archimedean property 1 holds these equalities. So this is proven that, therefore, proven that the Archimedean property 3 is correct, right? So after we learn about the Archimedean 1, 2, 3, we can learn about another extend theorem. Theorem 2. For every real number c, there exists an integer n such that n smaller equal to c smaller than n plus 1. So it's quite institution, right? It's a very natural way, seems like it's correct, but how are we going to prove it? So let's the c in our real number by the theorem, Archimedean property 1. So the Archimedean property is very useful. There exists a positive integer k such that k larger than c. And there is a set S which is also non-empty and bounded above. M in the Z and M is smaller equal than C. So choose n to be the largest element in S. So we now choose n to be the largest element in set S, which means n is smaller equal than C, right? Because in the S and the M is smaller equal to the C. So n also should be smaller equal than C. Yeah? And from this case, we know that n is the maximum of S, right? And which shows that n smaller than C equal than C. This is very logical. And however, we know that n must be larger than n plus 1, right? N must be larger than n plus 1. So, but n is smaller equal than C. So these two we combine together, so we will get n smaller equal than C smaller than n plus 1. Therefore, this proves our theorem 2. So also a very easy proof by Archimedean property 1. So let's see about the Archimedean application. So for any real number x and epsilon larger than 0, there exists a rational number q in the rational number such that x minus q is smaller than epsilon. So this is a very quite hard proof and also it leads to the density, another topic by the Archimedean property. So let's prove it, this theorem. So it's the application of our Archimedean property. So let the x in our real number and epsilon larger than 0. By the theorem, the Archimedean property 2 shows that for any positive integer n such that 1 over n is smaller than epsilon. So it's a very hard proof because we need to set equalities in equalities, which is 1 is smaller than nx. So we consider that the nx is a real number. By theorem 2, we know that there exists integer m such that, just now we learned the theorem 2, we know that there exists an integer m. So m and nx is a real number. So m must be between the nx, right? So m smaller equal to nx smaller than m plus 1. This is what we get. And then the purpose our aim is we need the x, right? Because just now we know that we need x minus q. So q is a rational number which can written as m over n. So we look back here. We divide n. So here m over n, and then here m plus 1 over n. So we now consider that, so we let that q equal to m over n. So q smaller equal to x smaller than q plus 1 over n. So it's very makes sense. So now we minus q in both sides. So here is 0 and here we get q and then here we get 1 over n. Why we do this? Because from here, we know that here have a absolute value. So we need to let the x minus q inside here, inside the middle. So now we know that. So just now we write this. We need to absolute the x minus q. So let's absolute it. And we will get this, which very makes sense. So we need to let the, because from the property 2, just now we say we need there is any positive integer n, which is here, and such that 1 over n is smaller than epsilon. So here is gonna smaller than epsilon, and we prove our proof is done because x minus q, absolute value of x minus q is smaller than epsilon. So our proof is done. Therefore, it is proven that every real number x and epsilon larger than 0, there exists a rational number q such that x minus q is smaller than epsilon. So this application of the Archimedean property is very useful in something in approximation like this. So approximation of real number by rational number, which also leads to the density of q in R in this application. So it leads to another topic also called density. So this is what we learned today, and bye.